I'm going to briefly take you through the solutions for getting the force on Q1 due to Q2 and Q3, and getting the force on Q2 due to Q1 and Q3. So I've broken those up, and I've indicated the direction of the arrows, and I think that this is an important step when you're doing electrostatics types of problems, just drawing out the arrows, because it can be confusing when you're using the equations. You can get lost, forget what your answer should look like. And if you draw the arrows, then you kind of have a good idea of what direction the forces should be in. And I'm just going to make a note, not quite sure what that was for, but that's going to be the negative direction, that's going to be the positive direction. So when I look at Q1, I should notice right away that I should get out a negative answer for the force that's involved. And I have these two forces. And one of the things that we had talked about briefly before was that if I'm looking for the force on Q1 due to Q3, it doesn't matter that Q2 is in the way. I can basically ignore, if I'm looking for how much of a force does Q3 exert on Q1, I can ignore the fact that Q2 is there, and I can just find out what that force is. But then if I want to find out the total force on Q1, I have to take into account what is Q2 doing to it as well. And so that's what I'm going to do right here. So I'm going to have the sum of forces on Q1 equals the electrostatic force from 2 on 1 plus the electrostatic force from 3 on 1. And a lot of this will be similar. I'm actually going to call this R. And this will be R as well. And that's going to allow me to just make it algebraically a little bit simpler. So I'm going to have now K, Q1, Q2 over R squared times R hat, which in this case is just -1, which makes everything work out nicely, because if you recall, R hat stretches, and it's actually, if I draw it to scale, this is what R hat's going to be, because it's going to be equal to -1. And if this was only 0.35, then it's going to be quite large in comparison. But it's just unit 1, magnitude 1, but it's going to be in the negative direction from the source of the force to the object of the force. So there I have my first part, and then the second part is going to be plus K Q1 Q3 over 2R squared R hat. And this is also going to be -1, because if I look at this, it's going to extend from here all the way over to somewhere over here. That's going to be the R hat for that one. I know it's a little bit messy, but hopefully you get the idea. It's still going to be -1. Now you might think, well, that's going to cause these forces to be the same, but remember that this is a negative number here. So I'm going to get a positive out of this. At this point, I think it's pretty straightforward, and you can solve this problem without too much more trouble. You just plug in the numbers and you solve. One of the things that they did do is they wrote that it was 74 microcoulombs. That's the same thing as 74 times 10 to the -6th coulombs. Now if you just look briefly at this one over here, solving for the forces on Q2, one of the things that's interesting is that there's going to be a repulsion from Q1 on Q2, and there's going to be attraction from Q3 on Q2. So they should end up giving us the same direction. This one will cause a slightly bigger force than this one, simply because of the charge. It's a little bit bigger of a charge. If we look at the first case when we were looking at Q1, Q2 is the smaller charge, but it's also closer. And that's going to make a big difference because of the fact that we have 1 squared here and we have 2 squared here. So this is going to be, even if these were the same size charge, Q2 and Q3, the force exerted by Q3 would be 1/4. Well, it turns out that this one's almost twice as big, but it's twice as far away, which means it's definitely going to be the weaker of the two forces. So the net result is going to be that Q1 is going to experience a net force off in that direction. But getting back to charge 2. So for charge 2, we have the force from 1 onto 2 plus the force from 3 onto 2. And when we look at what this then indicates, we'll have K, Q1, Q2 over R squared So nothing's changed. This is actually the exact same value here. The only difference is that my r hat is 1. The reason being that I go from the source of the force all the way over towards the object of the force. And then we do this again, and we have Q2, Q3, which would give us a negative, right? Because this is going to be a negative number here, divided by r squared. I almost put a 2 there, but it's still just r away, times -1. The reason being because now we're going in the opposite direction from the source to the object of the force, but a negative and a negative give us a positive, and that's how we wind up getting a positive magnitude out of this. Hopefully that settles how you would go about solving a problem like this. It's a straightforward application of Coulomb's law. The only difficulty is that sometimes people get messed up by the fact that there's a charge in the middle there. They think that it might affect the force that this one exerts on that one, but that's not the case at all.